All right, so I'm going to open up a couple of links on this for you guys to show you a couple of other items that I found that I think are decent resources, especially when it comes to backprop, both visualization and kind of understanding what's going on here. We have a project upcoming, okay? And it's one that I'm adding to the course because I think it's interesting. Some of you have already taken on an attempt to try to do this, which is to implement a neural network on your own. I said I mentioned to you guys I found code, made some modification for it. It's working, it does what it needs to do, but I want to try to make sure I put clear instructions together for you. What I'm going to ask you to do along with that is to analyze each of the functions that are called in that program, effectively saying what's happening at each of those steps and describing to me what the output of that is, like what it takes, like effectively what it's passed as an argument and then what it returns out of that system. I think if you have that sort of under your belt, you'll have a good perspective on the second portion of the assignment, which is I'm going to have you guys practice with taking like a sample neural network layout and annotating it and then generating the matrix format and then showing me at least one step of the back problem, all right? The reason why I want to do that is I know it seems like I said busy working, but at the same time, each topology has its own kind of different setup for it, and just being able to show maybe 3 links back and how those 3 links relate to those multiple outputs summationally relating back to a previous network and update state, I think is a good demonstration of your knowledge in general. So that's probably about as far as we'll go with the mathematics on our midterm exam, as far as what I might hope for you, other than the 2 proofs that I'm going to do, okay? The reason why I say that that's not the only thing we're going to do as far as math goes is the 2 proofs will have stuff that's in them that's where the matrix algebra comes from, yes.
When is the midterm?
Yeah.
I know.
I'm not sure,
I know.
okay?
Okay.
Do you need to know now?
No.
Well,
The midterm is...
I would like to know now, but if you don't...
Let me explain to you something else. I want to tell you guys how I'm planning on doing it. I have a point at which I say when I get through that material, that's when I will be done and ready for us to do a midterm. I will provide you with a minimum of 2 weeks advance notice.
Okay,
right?
thank you.
I always do that, all right? So that's the truth.
Right.
So it's at least plus 2 weeks from where we're at right now,
Okay.
which would make sense because we're at week 6, right?
Right.
So, but I'm gonna say that we kind of missed some stuff. I'm having to kind of try to play catch up a little bit for at least a week off. And I'm thinking I would rather go into week 10 or week 11, preferably, all right?
Okay.
The reason why is we call it midterm, but at the same time, most of what we're gonna be doing for the remainder of the semester is gonna be discussing and filling out some of the things that we're gonna actually talk about today. I'm gonna give you guys a peek forward, and then at the same time, I'm gonna be doing some stuff in the background. We're reviewing videos. I have 2 videos planned. One is a walkthrough video I started it, walkthrough video for the programming activity, and then the second one is the proof that includes all of the matrix form versions of the calculations. Really, I've already shown them to you for the most part. I've shown them to you kind of structured long form, but I want to work them out and walk through them so you guys know those. Having that under your belt, having that math, and knowing where the relationship, how the Laplacian creates a relationship between the gradient and the Jacobian and Hessian, right? The gradient of gradients, that decomposition and the eigenvalue decomposition as a matrix assessment is important to the internal calculations of the weight data space. But as far as it goes, what are, when we get there, when we get a little closer to saying we're ready to put a cap on that, I will for sure let you know. So you have a solid answer on date for that, okay?
All right, thank you.
Okay. You put me on the spot.
I'm sorry.
No, it's okay.
I just wanted to.
I try to avoid that question whenever possible, because I would say in some senses, I I'm passionate about what I do, and I think you guys can tell that. I get excited about it, and I'm always trying to improve upon it, and always trying to do something different. But at the same time, that also makes me a little scatterbrained, okay? So the first time I'm rolling through this stuff, I'm not saying I'm entirely flying by the seat of my pants. I have it as a rough tentative schedule, but I'm reflowing some stuff because what I'm recognizing is something that was mentioned to me is sometimes people learn better from doing and implementing than they do from any of the practical stuff. Theoretical stuff, right? So the practical stuff versus theoretical stuff, they would prefer the practical because it elucidates the output. I think in some senses, I kind of did that for you first, where you started off doing that exercise with the TensorFlow Playground, okay? What we're then going to do is we're going to tear in all the way into the code. We're going to build the code that does the basic works for it, and then we're going to actually deploy TensorFlow, and we're going to work with real data sets for a little while, okay? And that's going to be doing things like selection and topology. I'll talk to you more about topology selection as far as like how many nodes in a layer, how many layers total, those kind of considerations. There are rules for that, but I will say that that's the portion where I have to get kind of real on it. Follow with me real quick. Let's look at it. Let's look at this website. I know if I don't show you the website in class and make a big point of it, nobody's going to look at it. Okay. So the reason why I'm doing this is because of that process. So I'm going to go ahead and click on Build My Own Network. Over here on the left-hand side, right, I have data points in the system, and then I have hidden layers, and then I have nodes per layer in this consideration, okay? So if I just build that output, it's gonna go ahead and build this system, which we've already seen how this works. But the interesting part of this is previous to the update steps with TensorFlow Playground, how much were we able to step through? One full cycle, okay? This one does it really cool. I can choose to do for a single node, for a layer, for an example through the whole process, or one full epoch of the system, or the full run of the whole system, whichever I like. So if I do the node perspective, what happens? It actually shows me what the node output was. I prop to the next node, and the next node, run output, right?
That's cool.
If I do it whole layers at a time, it does layer, output, right? If I do it for an epoch, notice, it's actually updating the weights, right, at each epoch, and I'm able to see how much it's updating each weight at each epoch. Now notice, I didn't get up to a point at which I changed the weights in the system until what? Until the epoch level, right?
Yeah.
All of these other operations, if I go node by node operation, it'll keep running through until it does the whole set, and then it will do the weight update eventually. But we know that there's node example numbers for cycling. It's going to take several steps in order to run through the whole thing until it does the update. So if I wanted to calculate how many nodal updates for how many samples I had, I could change this number of steps, and it would run through and show me all the steps for each of the node propagations through the system. So if you need to know exactly what's happening at every single step of the process, watching it through the workflow in order to get it, this is like a GIF you can stop, and proceed one frame at a time, okay? So this one's really nice. The other thing you can do is this one right here, which is full, and that is based upon the numericals that we put over on the other side. If I click full, notice what happens. It'll run the whole thing, run the back prop, and run it until the remainder error with the output space is minimized for each of the examples provided above. I can add additional examples, and I can change what the examples are by going into the panel over here on the left-hand side, okay? So I can actually add a record to the system and then input data here. So you can also add a field. What happens whenever I add an output field? Add an output. Okay, I have to put something in. What am I doing?
I think it was.
Did it say something wrong?
I think it's highlighting it in
Oh.
red. I don't know what that means.
Didn't it?
Oh.
It did. It worked earlier. I don't know what it was.
Oops.
Well, theoretically, you can add outputs. So what would happen? Let's just go ahead and think about it, right? So since it doesn't do the thing, I'm gonna reset it and see if I can get it to do the thing. But what would happen here if we got this to work properly? I think it's actually doing this because I made a mistake on the record number. Check here. I don't really know what's gonna happen with this. Okay. No, it doesn't, still not doing it. I'm not sure why it's not doing it.
Can it only have one output?
No, it actually allowed me to do multiple inputs and multiple outputs last time. I'm not sure why it's not checking it now.
Uh-oh.
Hidden layers. All right, here's another thing we'll do. I'll just go ahead and do this so that we can see what it looks like for additional topologies. But I wish this allowed you to do something like actually add records to the system. That would be really nice. So one of the things that I would say is maybe it's checking that the numbers that I'm putting in, I put decimals in previously. Maybe it's checking that the numbers that I put in actually make sense, or whether they're closed with respect to the notation. Because I think I'm just punching in binaries now. But if I wanted to add the number of hidden layers, watch what happens. I get drop downs for the number of nodes in the layer, and I can adjust each layer to be able to have its own number of nodes. Okay.
Holy
So
cow.
this is really cool because it allows us to do what? We can watch through the network and see which individual elements are actually going through the system, and we can watch the connected weights for the I/O. Okay, so if you need a little bit of extra visual in order to make this all make structural sense, this is a really nice tool for you. It just, at least with regard to just setting up an output. Now, training complex data set, I do think that there's an upper limit. I tried to put in, I think I put in like 20 or 30 samples one of the times that I tried, as I was copying and pasting data from another data set I was doing it from fish rockers, right? So I just did the 4 to 1 for 4-1 classifier, and I was able to add those 4 features to the one output. But I think I was only able to add like 20 or 30 samples. Okay, so once this panel fills up here, and it won't let you add any more samples. But it'll let you build a much more complex network than is any way possibly warranted for the amount of data we have, right? Do you need this many layers in order to be able to classify 4 samples?
No.
This is all just about the topology, and it's about how the topology propagates. So this is way more complexity than we actually need, but it's really nice that it shows us and allows us to highlight and look at the components of it in a slightly different way than what we had previously, which, as I said, the advantage here is that we can do like multiple nodes, multiple runs, multiple examples at a time, and look at the update process for running single examples, or then full epochs for the full weight propagation of the whole system. Okay? And notice what's happening is I keep running through it. I keep running 3 runs at a time. I can do batches of like 10 runs at a time. I notice that it's not really doing anything.
It gets stuck at some point, yeah.
It's gonna sit there and it's gonna try, right?
Yeah.
But one of the things that I want you guys to note with this is between the dimensionality of the input and the output, it makes very little sense that I have a network of this level of complexity between it, right? If I had an input that had substantially more dimensionality, then that might make a little bit of sense that we're adding more complexity to the network as the flow goes forward. But this network is so complex that with the small amount of error that we're receiving on the output side of the system, remember I was talking about the idea that during the backpropagation flow we have a little bit of an issue through that process of the partial differentiation. Notice that the further back in the system, the amount of error that each individual node is getting as being a component of the total error of the system is smaller and smaller, because effectively, if you look at it this way, each individual element in this node is what? It's contributed to by 7 values come forward to integrate to that node, right? So we have 7 relative errors at that nodal location. That's a relatively decent value, but we have 4 elements connecting to the previous layer, to that particular nodal aspect. So that prop is going to go 7 to 4 prop. But what happens then for this node relative to the error at this hidden, right? I'm going to go from that node to that hidden, and we're going to watch. So this goes for hidden 2, right, up to hidden 3. So hidden here, hidden there, hidden here, right? Prop back. 4 divided over 4 again, or excuse me, over 5. So 6 over 5 over 4, right? So we have 4 nodes that are transiting 6 to 5, meaning that it's 6 nodal points for the activations back to 5 through that activation. So it's chaining back through that process. If you think about there being a small amount of error here, and then it's chaining back through, it's being diverted through a splitter, right? Effectively like a pipe splitter, if you will. Think about how much, if you would say the selection pressure were kind of the analogy that we used with the shower water kind of process. The pressure is being diverted over so many nodes within the layer and going through so many nodes back or layers back in the system that by the time it gets there, there's not really any pressure left. It's just being spread out so much, trying to split. The optimum goal of backpropagation is what? I've said this before, spread the blame around, right? You don't want anybody to have to be responsible, so just spread the blame around so that everybody is equally complicit in the output. But utilize the estimation of their localized gradient as their instantaneous value of likely error, right? So what happens whenever the gradients start to get really small? We call that the vanishing gradient problem, right? We say that as it gets close to the minima, the amount the gradient is actually affecting the system is small, thus the amount of error that that individual weight is going to be changed by is also going to be what? Very small. So initially, we have lots of adjustment that can happen because we have quite a bit of error to push around. But as the system starts to converge to relatively small error, that small error has to be spread over many, many people based upon their individual gradients, which are also doing what? Going to very small values. So that whole process says that the further back you get in the chain, the more problematic that is. We call that the vanishing gradient, right? The gradient effectively does not, or the utility of the gradient effectively vanishes to a point where you're multiplying by such a tiny number that the amount you're updating is what?
Like
0.
Effectively 0.
Yeah.
Effectively 0. The reason why is because the multiplication probably falls off of whatever the bit sizing we have for the amount of memory that we're allocating to that, right? So each of these weights can only be whatever the amount of bit sizing that particular weight can be represented by. So if they're a 16-bit value or an 8-bit value, they can only go down to a certain number of decimals before the calculation is actually, the product is actually on the right-hand side of that and falls off. The other thing is that it learns so slow that you're like, oh, come on, you know, it's like hundreds of epochs go by and it's learned almost nothing, right? It reminds me of some students that but no, I didn't say that. I didn't say that. No, that was me. Okay, this one I opened that one. Okay, backprop explainer is not quite as high utility, but it has some interesting components in that it shows you how the weight and the bias characteristics affect the error, right? We can show the difference between weight and bias and the total of the loss function output. We can also look at the notation of the cross entropy, right, and see the notation and loss. It shows you the effects of the outputs on individual neurons as the value of the error system is adjusted for the weights and biases, right? As well as shows you a little bit about the actual mathematical products in the system. And then the last component down here in the bottom is kind of a miniaturized version of the TensorFlow example, but one that we don't have in there, okay? And the cool thing about this, the reason why I added it, is this is a function approximator. What is that function that's being shown there in the dots? Right? It's a sinusoid.
Sine wave, yeah.
It's a sinusoid, okay?
Yeah, sine.
So I said previously that I could utilize a neural network to approximate any form of function. So I should actually be able to make a neural network that fits to that. So if I start off with a bunch of compound linearities,
That's cool.
the system starts trying to find a solution,
It's getting there.
right? Notice what's happening to the loss?
It's yeah.
Jumping around now.
It's jumping around, yeah. It's trying to get there, but it's.
What do we think is the biggest component here? What might we do to try to fix that loss bouncing around the center? Nah, nice, good suggestion. I gotta attempt to reduce the learning rate, okay? Then I have to pump it down and start over again. What happens when I reduce the learning rate now?
It's not moving at all.
It's trying so hard.
It's trying so hard, it's like, I'm getting old here, come on.
It's crawling slowly to the solution, okay? I wanted to show you guys this because the immediate solution that pops in mind is like, change the learning rate, okay? Which with TensorFlow Playground, you can do that while it's still training, right? With this one, for some reason, you've got to stop it to select it. It resets it. I don't know why.
Is it getting faster as like time goes on? Maybe. No.
So there's an interesting aspect to it to where I do actually think, so let's do something. Let's look at this. What is the slope of this line? The slope of this line is how much it's actually learning per unit time, right? So the learning rate is how much the weights are being updated, but the slope of this line implies that there actually was fairly slow learning for a while, and then look what happened to it. It actually, the slope increased for a bit and then slowed back down. So you were correct, it was learning more quickly for a little while. Why?
It's finding all the values, and then
It's getting closer to the values.
Yeah.
It is, it's getting closer. It's finding the valleys, okay?
Yeah.
So if you think about this as a complex, rough surface with lots of little individual indentations, sometimes you're sort of traveling along like rough plateaus or regions that have a lot of rockiness to it, but then all of a sudden you come to an edge of something where the gradient surface, right, the error surface actually dips pretty hard. So if a whole bunch of values start to get really close to converging to the ideal positions, the system will go, aha, right? I found it, I started to find it. So the network, if you can think about it from a functional perspective, if the network is an approximation of something like the Taylor series expansion, you could think that every time it's adding a term that actually fits the functional approximation at that level, then it will successively reduce the error. So every time it's finding some subset of correlations between the weights through the I/O system that's improving its overall error from the output. So as a result, it's going to attempt to converge to that final position. Now what's happening here again?
It's flipping.
It's starting to flip around again.
Yeah.
Why? Bad tail behavior. This network is way too complex for this particular system.
Yeah, I was
right?
about to say.
It's too much. It's too many weights. Okay, so we can't actually change the number in the layer, I don't think, but you can change the number of layers itself.
Maybe yeah. Let's decrease the layers.
So if I decrease the layers, right, then I should be able to perhaps, let's actually try just doing a slightly higher learning rate. It's a little bit emotionally challenging to watch it learn at the lowest learning rate. Yes.
So in like a business setting, would having a high learning rate be okay if you're not getting the exact product, but you're getting a rough estimation of it? Because it's much more competition, it's like much faster you get an output.
Okay. We're actually going to talk about this at an entirely different time. Learning rate is a parameter, just like any other parameter. Oftentimes we actually want to start off with a high learning rate and then do what? Actually reduce it over time. So we want it to start off taking big steps, and then we want it to slow as it begins to approach the minimus, right? So we want it to get, if perhaps there is a small sort of locally graded local minima, we want to make sure we don't avoid those because they're still optimal for the local space. So we might actually have to reduce the step size in order to make sure that we find the ideal minima for the local space. The idea would be you're moving along, you've got several drops here, right? And then you've got one that drops down, but there's a spot in it where it's slightly deeper than the rest, but it's not very wide. So you want to decrease the step size, how much you're actually moving the weight, by reducing the application of the gradient to the weight update. So the learning rate is going to be reduced over time. There are a couple of different ways we can deal with the learning rate. It's interesting because if it's still learning, we want to keep it learning, right? So we don't want the learning rate to go to 0. So we can use, actually one of the mechanisms we use is something called momentum, where we are going to use the amount of change, or the second derivative of the gradient, to assume the velocity of change per unit to effectively keep the learning rate at a scale of how much we're actually getting out of every time we do an update. It will then slow down as what? You're getting less out of it per epoch. The idea is that you start off making big strides towards the final objective, right? But then as you get closer to it, you're slowing down because you don't want to run into the wall, okay? You don't want to run into the thing. That process of adjusting the learning rate is it's yet another parameter. So we talk about something that's called hyperparameter optimization. That is both how we select our learning processes, right? Which activations we're going to use at which nodes, and also how many nodes there are per layer. Also, perhaps the way in which the learning rate is being set or the way it's being scheduled. There's schedulers for those learning rates. Yes?
So in the other example, one of the parameters was tolerance. What is that?
And the other one?
Mm-hmm.
I think it's how much it's using for upper and lower banding of the activation function. I'll have to look at that one again. I'm not sure what it would mean by tolerance in that particular case. I'll have to look and see. Honestly, there's a couple of meanings for it, right? So you have slack tolerances, and then you have integral tolerances. The problem is that one is way more complex than necessary for the data set that it provides. I think it's good as a visual example, but I'm not sure I would encourage you to play with it much, because it doesn't really do much of interest. This one's kind of cool because it has some selections, but very fixed in terms of learning rates. It's only got 3 data sets, but it is a data set that shows the capacity for function approximation, right? Which, if you look at these, we have sine, cosine, and hyperbolic tangent for outputs. Now, can you make up pretty much any function with those? Absolutely. Right? Using those 3 functions, we should be able to approximate any waveform as a component of them. That is effectively what the Taylor series is doing. It is utilizing localized approximations of sinusoidal functions in order to approximate regions or additive components of a mixed model, of a signal that contains multiple sinusoids. All right? There's links to this on the slides, okay? But I'm going to go through, I'm just going to fly to the end of the slides, okay? Because I want to do something again at the very end. Let's talk about cost function operations again, because we didn't get enough time last time, and I want to make sure I get it clear for you. In order to be able to appropriately determine the amount of loss that each individual weight is contributing to for the system, I'm going to have to look at the impact that that weight has on the desired output, right? So the desired outputs, we have 2 cases of desired output in the strict binary system for 2 nodes being hot at the end. Whichever node activates is the hot node. Now, that's just an example that we're using, simple example, right? But the example that we had in the slides previously, there were 3 classes, right? So this one just shows 2 classes, if y equal 1, if y equals 0. But we could extend that to making the cost function a piecewise function that considers the relative cost of misclassification for a specific class sample within the system, as perhaps one class is more costly than another. Now, how do we determine what the cost function looks like? Oftentimes, we're going to utilize some form of probability density estimate and a prior relationship. Right? You guys remember Bayes' theorem? We had pi and we had f of x, right, or FL. So we would have pi, which is going to be the prior component, that is how many, or the predominance of that specific element in that class. And we have the f of x component, which is the density function characteristic. That is the likelihood of that particular value to lie in that particular sample space. So I can utilize an approximation of a density function approximation to provide my cost function, right, by saying that the samples that are lying towards the mean of each of the distributions are going to be increasingly likely to do those desired outputs, right? But what happens in the crossover regions? What happens in the similarity spaces of the correlation? We end up with a situation where one class, which might have a narrower prior, right, fewer samples in the system, is underrepresented structurally. So we're going to have to try to adjust for that with the cost system. We're going to have to penalize the network for misclassifying the minority sample. I'm using a lot of complex jargon, but I'm going to break it down for you here. When you have a population that includes a small number of individuals that are representative of one specific class, an identification of that specific class is paramount to your task objective, then including a cost function to be able to penalize the network slightly more when it misclassifies that specific class is beneficial to the overall outcome of your model. So by being able to treat different classes differently based upon their dominance or predominance within the space, their majority or minority status, or their relative prevalence within the system, can allow us to be able to still train networks that do not have perfectly equal numbers of class representations in the space. We said ideally, right, we want to train models that have exact equal numbers of the things that are at play. But what happens in that space? It fools the network into thinking that those two outcomes are effectively equally likely, right? So whenever you apply it in the real world, you have to rescale the network in order to be able to effectively respect that frequency of the components that are necessary. The example here is one that I think all of you guys can see the value in, and that is credit card fraud, right? What's the frequency of credit card fraud? Relatively low whenever you actually think about it in terms of the total number of transactions that take place. But try to train a system by regression, right, or classification, backprop, what ended up happening whenever we did that with logistic regressions and such. The dominant class would almost invariably win, right? If it was 99% of the data, that meant the prior was so much higher for the density output that we would likely see the system doing what? Err on the side of caution and just place it in the predominant class. If I have a choice between two placements and I see that this one is 99 out of 100 going to be the class that's going to dominate the space, then if the goal is to minimize error for every sample in the system, what do? Throw everything in there, because the few samples that are going to be in the other class, that don't matter. Cost functions allow us to control the network. They let us get our chair and our whip out and be a lion tamer for the model and say, back model, back. Okay, so that's what we're doing. A lot of times being a data scientist in the machine learning space is effectively being a data wrangler, right? You're trying to get it to perform, get it to behave the way you want it to behave. At the end of the process, we have what? We have our learning rate again, and we have now this comprehensive function which states the relationship between the update for our ideal gradient given this sort of more complex log likelihood estimate function for the two class outputs. Is this going to get more complex whenever you have multiple classes? Absolutely. But we also have the option to be able to have this done automatically, okay? So sometimes you can use different functionality, different methodologies to prescribe your cost function. But in this particular case, we can use something like simple log analysis, right? And where do we get the logarithms from? We got them from these being effective mirrors of logistic operations, right? So we modeled them logistically based upon functional separability of the classes. So this is using the priors of the classes and density estimates via a relative correlation component to be able to determine this ideal cost operational update, okay? Notice, once the cost for the appropriate class is placed in here, that means that the weight is being updated conditionally based upon which type of class the sample was. So there is a condition which we have placed on the update. That means that there are now two different update functions, one for class 1 and one for class 0, effectively. The reason why I say that there are two functions is they're composited together. It's just that one works when one part of the function is on and the other works when the other part of the function is on, right? We see that as either being y or y minus 1 for the activation of the logarithm, okay? Whenever I take the outputs of the system, right, for that last part of the ReLU model, right, and run it through the last series of weights towards the output of the system, plus biases in the term space, I get the last vector output, okay? Remember that vector output being categorical is going to be error based upon this cross entropy analysis, product for the likelihood of inclusion within the class versus all other classes times the log likelihood of the output classifier for the output space, okay? So I calculate this whole long log function, right, this long log function here, for each of the weights relative to the likelihood of it corresponding to that value being present at the output. And what do I get? An error that is in 3 parts, component level, for each of the relative log contributions of each of the errors to the total error in the system, which I calculate as this 0.985. Now, which of these two sets of numbers, or which of these two pieces of information is more useful? The total error in the system, or the component-wise errors of these elements? The component-wise errors, right? So even though this number exists and provides us with a global error for the system, it's not as useful as an actual explanation of where those errors originate from. So sometimes whenever we're talking about the accuracy of a model or the total error of a system, you've got to understand that the error can be in parts, all right? You guys remember the receiver operator characteristic and the confusion matrix? Okay, we're going to use them again. We'll get them out whenever we start talking more about classification. But we would consider this as effectively 3 errors for 3 relevant classes for the output, right? This is the relative level of error each of the contributions the output have to that misclassification process. And the cross entropy allows us to then adjust the weights for the imprecision of each of the class outputs. So it then becomes that standard relationship. So cross entropy does what? Automatically generates a cost function based upon the relationship between the class component and the output component of the system. We say it is the entropy of comparing one class versus the rest in all those configurations, like 1 to 2, 3, right? 2 to 1, 3, 3 to 2, 1. So that entropy, that process is one versus each case, one versus the rest, in the quality of it to be able to appropriately classify the output. We only have one sample here. That's the real problem with this feed-forward process. How do you train something with one sample? Well, you overfit majorly, right? So when you do the update, you're just fitting to just that one sample. But the argument being here, if I had multiple samples, then I would see the cumulative error in the system as a result of each of the relevant classes of the examples that were provided, right? So the cross entropy would then analyze each class and calculate the loss function relative to that class of the system. This is just one that utilizes the characteristics of the output with respect to the total samples in the space. So this 1 over n is the control for the average categorical cross entropy error within the system. All right, we talked about the differentiation. We talked about the backprop, all right? I'm going to go forward all the way to the end of this because I want to get to this idea of the error output for the expectation, okay? What happens here at the very end of the system is the last and most important element that we're concerned with in the backprop cycle. We have chained each set of the weights back, right? We've created a matrix which conforms to the relative expectation or component of error as the partial of that weight with respect to the error of the next component of the next node and the next node of the next node, right? Remember, the inputs of any given node are effectively the outputs of the previous layer, and you can consider that output of the previous layer to look a bit like the feature vector for the first layer, right? So any given hidden layer within the system effectively looks back at the previous layer as if its inputs are features, right? So each layer, when it activates, it's presenting features to the next layer. So it's a feature extraction process. What do I mean by extracting features? I mean, there are real-world constructs, shapes, interaction between those shape components, elements of surfaces, curvatures, lines, all of those things that we think of as being what makes up natural objects and natural systems, right? Each neuron, each node, as a composite of the weights, effectively transforms its input from the original weight vector times the input and activates based upon the presence of some feature that it's designated to identify. And it will activate stronger if it finds the feature that it's really interested in. So networks effectively try to find patterns. We can think about numbers being put together in patterns. We see numbers are circles, right? A circle above. Circle at the top means what, right? Could be a 9 or an 8, okay? You need the other circle in order to determine it. But circle at the bottom, okay? We know a circle at the bottom. There's no circles at the bottom then. See, it's an 8, okay? But just a circle at the bottom, what is that? Could be an 8 or a 6, right? So just seeing a circle in a position doesn't definitively tell you what that particular number is. However, if one neuron was set up to detect circles for that region, and another neuron was set up to detect curvatures at the top, another one set up to detect lines across, right, and lines on the side, then we could have them activate and say, hey, a line at the top, curve at the bottom, curve on the outside, that's a 6, right? Circle at the top, circle at the bottom, that's an 8. Circle at the top, line at the side, that's a 9. If we could get it to do that, that would be beautiful, okay? But we can't always get it to do that. Why? Because if you go and look at something like the MNIST data set, which we're going to play with, it's handwritten digits, what you're going to notice, they're incredibly inconsistent.
Exactly.
Okay? There was a homework example, and I think I might give this to you guys just as a little exercise. And that is, write out a word or write out a series of words several times, okay? And then trade them with a friend and look at them and see how consistent the representations of the writing of those words are. Whether there's common features between it that would allow you to be able to say, hey, could I make a model off one of these that would allow you to identify the remainder of them? Is there enough internal consistency? And if we think about it from this process, why can't we just use the fixed algorithmic model to identify numbers? Circle, edge, line, 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 right? That should be easy enough. The real world is too variable, okay? The real world requires adaptability. So in truth, at the end of this process, why do we need the backpropagation? Because the backpropagation adapts. This is where the model adapts, okay? It had some previous understanding, and then it adjusted the understanding based on the evidence. Our brains are networks like this. They're backpropping, they're integrating, they are taking the information from the natural world and adjusting small tweaks to the process. As we age, that process slows. Learning rate decay. Okay? It's true, it really is. Okay? The plasticity of the system slows, thus more examples actually slow the process of this weight update. What happens whenever you get into millions and millions of samples? What if I throw one additional sample in? What happens to the total error? Very little. So after a while, these systems begin to converge on the information that they already have been presented with. They functionally converge to the bias spaces, which are the natural distributions of the samples that they were originally trained on, right? They fit the variances of their data sets. Models like this are nothing more than the functional distillation of the components that they're made up of. I think I told some of you who were in my ISL class, the highly flexible models are like water, right? You pour it in and they assume the shape of their container. Neural networks are the most liquid form of any kind of model you can assume, right? You pour them in and they will assume the shape of a sinusoid, eventually. They are loosey-goosey. Okay? They don't have any spine whatsoever. They're going to do whatever they're told to do. All right, so what I'm looking at here is actually the process by which I'm going to achieve my understanding of the relationship of the partial of the whole input of the system relative to what? One weight, one specific weight. Now, could I represent this as a weight vector for the entire layer? Sure. Sure, I can do that, because I already did it as a matrix form. So I could then show the generalized form of this whole system for H of 2 relative to W star of that layer, right? And then look at the quality of W for the input layer as a component in general. And then you can calculate this ratio for each of the weights at that layer that were fed into by that particular node component. So this last piece is what? My attempt to understand the relationship of some output to some weight for each component for each of the elements in the layer, right? So this is from K to L relative to O3 in. What is O3 in? This is the input for the last activation function. Notice I'm not necessarily doing this from O3 out, right? I'm not doing it from the soft max activation function operation because I've already backpropped that. I've already figured out the amount of error relative to the softmax op. This error has been propped through the first activation. Remember, we have three things we can kind of adjust here. We can adjust the component of the weights, we can adjust the biases, and we can adjust the connectivity. Those are really the only things we have to play with. The activations are a little fuzzy in that perspective, okay? The activation can be adjusted, but think about it this way. If you adjust both the weights and the integrator and the activation at the same time, what would happen? You're moving too many things at once, all right? So we're going to leave the activation function alone. It's going to be centered around its mean distribution, and we're going to then change the inputs to more ideally summate on whatever the activation operator is. So the activations stay the same. Once they're differentiated, they're what they are. So we push them through the differentiated versions of the acquisition function. We get relative contribution of the activation to the error, which is what? It's both the summation and the activation as a component of the error. But we're mostly going to be taking the input as the relationship for the error in the subsequent layer. So, if I take some generalized form of the discriminator for WKL, right, and I write it up as the error with respect to each of the feeding elements of the system, right, error of 1 for K1 to L1, error 1 K2 L1, error 1 K3 L1. This is the same, this is the first order error, right, because there are three errors to consider here. Previously, when the first time we did the backprop, we did it for one error. That was vectorized. That was a error vector, right? Now we're adding an error tensor. We have an array of errors. Each weight has now a contribution of error to each of the three outputs. Thus, the change in each of the three outputs will require the summation of those error updates to be propagated to that individual weight. So there is one set of weights that will be targeted here, right? K1, K2, K3 relative to L1. Those are the three feeders for L1. And then likewise, K1, K2, K3 for L2, and likewise for L3. These are just the three errors for three weights. Why do I have 9? Why are there 9 values?
Because you're counting the different layers as well.
So think about it this way. K3 to L2, right? And K3 to L1. Across this axis, this is all the ways in which K3 connects to L, right?
Yeah.
The second one is K2 to L, K1 to L, yes?
So as the network increases, like this increases quadratically.
Yes, it is a naturally exponential systematic relationship, right? So it continues to improve, it continues to geometrically expand at that rate, systematically geometrically expand. It's not a strict quadratic operation because we're going to break that when we go into CNNs, right? But for fully connected networks, it is, yes. Okay, so as long as everybody understand where these are coming from, why we have 3 weights, okay? Because that means that each of the interconnects, that means each link between each of the elements in each of the node characteristics bears the weight of 3 errors, right? 3 errors will backpropagate to it. What happens whenever there are 4 elements in that layer? It will bear the weight of 4 elements in the output. 5, 6, 7, whatever components in general, that item will continue to inherit the relative weight of that particular output error, okay? All right, the final system here consists of the actual update process here. The actual update process is what? The weight minus the learning rate times the relative contribution calculated from this system. This uses the value LR, right? We also use mu, right, as a learning rate approximator. So we can use mu, and we can use lambda. I've seen lambda used before. You can just say RK or LR2, right, rate of increase. But notice the learning rate is 0.1, right, so that's easy to be able to tell. We say product of the approximated partial of the weight with respect to the system times the learning rate is how much we're actually going to change the weight. So the vectorized version of the system here is the original system, right, modified by the backpropagated error relative to the learning rate in that structure. Everybody got what this last slide was talking about? All right, it took me way longer to get through it than I thought it would. Okay, so anyway, I'm done with that for the moment. I'll put these slides up for you. Let's talk this real quick, and I'm going to go through this fairly quickly, right? Obvious.
There's a lot.
Come on.
Yeah.
What? Look hard?
It was a nice
It's all
one.
gray? Okay, so you're not red-green colorblind, you're just actually colorblind. Okay. Yeah, I think my dog's colorblind. Anyway, thanks. Made it even harder. All right, let's go forward a little bit. We're going to talk through most of these. They look intimidating at the start if you haven't seen a few of them in the past, but once you've seen them, you go, they're all basically the same thing. All right, they're just structural components do make a bit of a difference in how these are put together. So let's talk about a little bit about the beginning of these processes. Some of the earliest networks, or at least connectivities of components, were part of the Markov chain systems, or discrete time Markov chains. Everybody remember what these do?
It sounds familiar.
Connections between Markov components are weighted probabilities of the likelihood of traversing out of that state. So each of the components is a state. Each of the connections between the states is the likelihood of the current state traversing to the successor state in the system. So here, the connectivity of this Markov chain would be complete, right? Except for one of the problems with it is we don't see the cycle of dwell time, right? We don't have the likelihood of the system staying in its current state. So this implies that this particular chain would have to do what? Constantly change, right? It doesn't have any likelihood of staying in its current state. It just has a likelihood of moving to any other given state within the system. Yes?
So it's a so if everything is connected with each other, like it's an infinite loop, it's not going to end.
Yeah, absolutely. That's kind of the whole point of like state machine operation, right? We want to start it up, and sometimes you can have a state machine, right, where you have some node on the outside here in the initial start position, right, and then it feeds into a state machine where we might have connectivities like that. Okay, this can be a directed component, such that as soon as the system is primed and we move into the state 1 from the state 0. This is a power on self-test for your computer, right? Post when it comes up and says, Dell or Asus or whatever on the screen, right? When it's doing that, it's actually doing some stuff in the background. It's saying, let me check and make sure, get my sheet out and check and make sure all the components are connected and responding, right? Do you have to do that again after the systems start up? No, you don't. So the goal is to do that state process once. So the connectivity implies the functionality. How is this related to neural networks? Show you. Hot-field networks were the next version of this system, and they are effectively the neural network equivalent. All elements of this system operate as edge nodes, and the nodes are both input and output systems, except for these are strictly binary operationally designed. The next version of this system was called a Boltzmann machine. Boltzmann machines allowed the input layer, right, and the output layer of the system to where nodes were bifurcated for being I/O, right? So this was distinct input nodes and distinct output nodes, but still fully connected. There's a huge problem with Boltzmann machines. How do you train that? What's backprop look like through a circle?
Yikes.
It's a cyclic decay, right? It is a spiral. You start with the propagation, what happens? It spirals through the connection, and the decay process, the gradient, vanishing gradient, eats it, okay? It's a snake eating its own tail, the Ouroboros of networks, okay? Jeffrey Hinton, one of the big granddaddies of networks, all right, was one of the actual guys that worked on this stuff back in the 70s, right? Their trick, their fix, was what we've been doing, okay? Two traditional operational feed-forward networks, FFN in the left-hand case we call the perceptron, right? We've used that term beforehand. And then the other network we're going to call just an MLP, right? A multi-layer perceptron, or just a feed-forward network, FFN. These are also just called ANNs, artificial neural networks. So if you've ever seen ANN in a write-up terminology, you'll see ANNs. Notice it's fully connected along its transverse axis, right? Along the forward propagation axis, full connectivity. The restricted Boltzmann machine is actually a representation of the collapsed interconnectivity of the Boltzmann machine that removes the connectivity on the edges for the output and the input nodes. Notice the output and the input nodes in a restricted Boltzmann machine are not connected to each other. So simply by going through and clipping the connections to the output and the input nodes, now it works. Now you can use backpropagation to train the I/O layer and train the weights in between those connections. So if there is any off-axial connectivity, right, or interlayer connectivity, you can use it as functionality, but it's problematic in the long run for the propagation of the gradient formulation, which we're utilizing as a methodology for the training process, okay? If you guys discover some new way to train a network that doesn't involve the chain roll and the backpropagation of the gradient estimation of the Laplacian of the Jacobian to get the Hessian, then good for you, okay? Because you've solved a problem we've been dealing with for a long time. But at the moment, there isn't actually a core solution to tell us how to do an unrestricted Boltzmann machine, right? You must clip some of the interconnects between the outputs. Weirdly enough, not all systems actually look like this. Many look more like true Boltzmann machines, because sometimes the output of the systems are actually dependent on one another or have component connections to each other. So this is a flattening of the natural world that makes it feasible for us to be able to do closed form solutions of the I/O and create logical outputs for the actual numericals of the error, but ultimately still constrained, okay? Radio basis function networks are an interesting animal, and for those of you who have looked through support vector machines, some of this will seem similar. If I have a probability density function estimate, right, I can use that PDF estimate in order to be able to create or construct a dimensional distortion of the input space characteristics as part of the hidden layer, okay? The hidden layer in an RBF function does not learn how to fit the actual input values of the system. It learns how to distort the space such that this becomes a binary classification process. This is a weird one, okay? This is a kernel up projection process. So if you were to think about that surface, that Gaussian, right, being transversely sliced by a hyperplane, notice what happens. The items above it and the items below it get separated on a radii, right? We call it a radial basis. So instead of utilizing weight integrations times the activation operators, we're going to use radial activation operators as part of the integration, right? And they are going to learn how to make that shape fit on that system. So they learn to locally approximate the probability distribution function of the system for the up projection of the data space into a new layer output. For complex surfaces like this one, right? We need multiple radial basis functions in order to be able to cut the data apart into each of the subclass groupings, okay? So when you have complicated systems, we're going to have to be able to make multiple radii, multiple basis function assessments, which means more complicated network. Autoencoders, we're going to go into more detail on these. I'm just giving you guys the flash forward in about the next 3 or 4 minutes. Autoencoders are really cool. They're capable of taking input spaces, condensing them to features, all right, and then generating output spaces from that. Notice these are fully connected networks that actually condense over their length. So as it goes forward, the number of elements in the layer reduces, and the amount at which the layer reduces in number for the number of nodes in that layer is the degree to which we're going to consider the network to have sparsity, right? How much we're trying to cram into the next layer. The idea of an autoencoder is that instead of learning to classify or to procedurally generate the outputs of the system, we try to see how much we can compress it and still be able to blow it back up, okay? This is like the plane, or like that boats they put on an airplane, right? So you take all the air out of it, right? Until you can't take it out anymore, okay? And then you try to blow it up again and see if it still works. This is actually very similar to the idea of like audio compression or spatial feature compression. These are used for compression networks to the effect that I attempt to compress it, right? And then I attempt to use the internal feature layer. I take the feature layer as the inputs for the next layer, and then I procedurally increase the number of nodes. What happens? It's reinflating it. So crunch it, and then reinflate it. Hopefully, at the middle segment, we have a version of the system which is minimally representative of the input. We're going to go ahead and do noise variational autoencoders. Okay, I'm just going to tell you guys. I'll go back real quick. Truth be told, variational autoencoders include latent distributions. They attempt to learn the intrinsic distribution of the sample components at the latent layer. So instead of having internal compressed component representations, they try to learn feature aspects of the distributional mechanics of the components of the system they're made up of. The difference here between the standard autoencoder and the variational autoencoder is that it tries to learn patterns, and those patterns are a bit like tokens, right? So if you're trying to compress text, you might compress text by memorizing whole words and assigning each word a token, or you might look at as trying to compress it by seeing groups of letters, right? A-N-D, right? I-N-G. I-N-G has high frequency in English, so using a token to represent I-N-G might have higher compression capacity than trying to use whole words for each token, okay? So the variational autoencoder tries to find things based upon the distribution space that maximize the compressibility of the representations. Representations will be a key factor. Denoising autoencoders, these are cool. We'll use these, we'll talk about them. They attempt to take noisy input, right? Badly degraded, that has a lot of stuff to it, and try to provide the output of the system as being denoised. These are a little different than our standard autoencoder, right? Because the features, the core code of the system, the chain of the system, is the compressed version at the center, the cleaned version of it. But technically, we may want to keep the dimensions of the original input, but remove the components that made up the dirt through the encoding process, okay? So the dirt was actually removed, and then since the dirt has been removed, when we try to reinflate it, there's no dirt left. It just reinflates latent space where the dirt was. Sparse autoencoders do the same thing, but structurally decompress. okay? Deep belief networks are going to be one of our last sort of high-end items, okay? These are the versions of fully connected neural networks that learn representations at different layer spaces. And we have operations between the handoffs of groups of neurons that were specialized operations like softmax operators in between the layers, and then drop layers and max op layers, okay? The last one, and this is the one we're going to get to eventually and do a little bit more talk on. I know this is probably the one you guys are excited about.
Yep.
And we're actually going to go past this, all right, because we're going to talk about a few topologies that are new, and we're going to talk about temporal topologies, like those that deal with recursion, right? So the next version past this is going to be recurrent networks, in which the output layer actually becomes a small portion of one of the elements of the input of the hidden layer, such that the state and sequence order matters, right? The example that's given in the place that I found some of the visualizations for this example says that there's a difference between cookies and milk and cookies, right? So the order of some of the statements matter in terms of how we might think about them if we're looking through a sequence. Not just the strict adherence or recognition of the token, but the order in which the tokens were represented. So by using a small amount of the past and feeding a small amount of the past into the current, we can keep track through recurrence of the operation of the system. All right, we're done for the moment. I will go through the rest of the zoo, all right? That's what we call it. This is the zoo, this is the zoo of the networks, all right? We're gonna go look at all the animals. And then we're gonna go in and we're gonna talk about the ecology of each one and proper care and feeding of your network, okay? So, I make this class silly, I don't know why, but I have fun with it. Thank you guys, I'll see you next week. Watch out for me trying to put up some stuff for you to start on that. You'll have about 2 weeks on this assignment, okay? I'm trying not to overcram you. I'd like to get it done and then do the TensorFlow version of it before we have our mids. So we're going to be looking at trying to do sprints on construction of networks alongside of doing some write-ups for the math that we've been working on, okay? All right, thanks.